Welcome to the third part of the lecture 1, which is devoted to studying functional analysis. Let me remind you that we are following the textbook by Bresis, Functional Analysis, Sobolev Spaces and Partial Differential Equations. I really recommend this textbook for any applied mathematician. And today we will continue doing some problems that are devoted to the chapter 2 of this textbook. So, after this short introduction, let me begin the lecture. So that's the next problem, and that's our first problem. So let me definitely start with this problem. So we consider two Banach spaces. There is a typo, of course. Let E and B be two Banach spaces and a bounded operator from the space E to the space F, which is also injective. We need to show that the image of A is closed if and only if there exists a constant C larger than 0, such that for every element x in E, we have the inequality that the norm x is smaller equal than C times the norm of A of x. So, solution. So, is closed. Then, image of A is a Banach subspace. Of E, and A from E onto image of A is a bijective bounded operator so by Banach inverse no. So let's open mapping theorem. It is an isomorphism. In particular, the inverse A minus 1 is a bounded operator. So we get, let me move it a little, there exists a constant C larger than 0, such that for every y belonging to the image of A, we have here that the norm of A minus y is smaller equal than C in the norm of y. And that means in particular, so for every x belonging to E, we can write it down that the inequality star implies that we have here A minus 1, and let's substitute y is equal A of x, So we can substitute here a of x smaller equal than c a of x. So where this was substituted to the formula star. Okay, and that implies exactly that there exists a constant c larger than 0, such that for every x belonging to E, we obtain that x that comes from this inequality here is smaller equal than c, and this is equal a of x. And we prove the first implication. So let us now prove the second implication, namely assume that, okay, let's go this way, and assume that, let's move a little screen, assume now, assume now that the condition star, so not star, this one, this condition star, so now this is condition 1, is satisfied. And suppose we have a sequence and call this yn is equal a of xn, such that the sequence converges to a certain y naught as n goes to infinity. We need to show that the image is closed, so that y naught belongs to the image of A. However, notice that since the sequence A of xn converges, it is a Cauchy sequence. And from the equality 1 implies that xn is also Cauchy. Indeed, for every epsilon larger than 0, there exists an n such that for every n and m larger equal to n, we have here that x n minus x n is smaller than constant c, and that one is a of xn minus a of xn. And since that's Cauchy, so we have here that for the fact that a xn is a Cauchy, so I can write it down epsilon. As you see, that implies that xn is also a Cauchy sequence. Let's multiply it by constant c to make sure that the constant is correct. Okay, so what does it mean? Since E is a Banach space, the sequence xn converges, and move it a little down, and there exists a limit. There exists an x0 not limit of xn is equal to x naught as n goes to infinity, and so by continuity of a, we obtain limit of n x goes to a x naught is equal to, on one hand, n, on one hand it is equal to y naught, on the other hand it is equal to x naught, and therefore y naught belongs to the image of A, so image of A is closed. Okay, that's the, and this is the problem B that we will be doing in this segment of the lecture 1. And as before, we are dealing here with two Banach spaces, E and F, and this time a bounded operator, just a bounded operator, and we need to show that the image of A is closed if and only if the following inequality, which we denote by number 2, is satisfied. That means there exists a constant C larger than 0, such that for every x belonging to E, the distance between the point x and the kernel is smaller equal than the constant C and multiply by A of x. So let me start and let's write it down. Solution. So, knowing that A is continuous, we have that the kernel of A is closed subspace of E, and we denote, we can consider, maybe simply we can consider the so-called quotient Banach space and we denote it by E naught. This will be just the space E divided by kernel of A. Let me recall that the elements of this quotient space are, put it here, the elements in E0 are the cosets. And those cosets we denote like x plus kernel of A, for which we have the norm and let me write it down. I write this as the norm of this cosets, kernel of A, and I put here naught just to relate it that this is in space E0, and by the definition this will be infimum, and this x prime belongs to kernel of A, and of course this will be equal to x minus x prime, and it is easy. One moment, let me raise it, and it is easy to notice it. That's definitely this distance that appears in our condition. So clearly the quotient space is the right space to work on this problem. So let me continue. Let me notice a couple of things. So first of all, we have the following commutative diagram. Let me write it down. We have the following diagram. So we start first with the space E and denote by pi the natural projection. This is natural projection on the space E0. Recall, this is the E divided by the kernel of A. And then we have this operator A and then the space F. And instead of writing space F, let me write here simply image of A, because that's where it goes. So that's contained in the space F. And now I can define it. Let's see, put it here, I changed to the, and I want to define an operator A0 from the quotient space. And for this, I will use the definition. So let me write it down. We defined A0 from E0, and it goes to the image of F, definitely, because by the formula that E0 on the coset will be just simply equal A of X dot. That's not the end. We need to first put here a little dot, call this formula star. The formula does not depend on the choice of representative. X of the coset X plus kernel of A. Indeed, put here semicolon and write indeed, if X prime plus kernel of A is equal to the X plus kernel of A, then this means, so X minus X prime belongs to the kernel of A. And we have that, and let me write it down nicely. A of X is equal the same as A, and now I put here X prime, and that's, write it down, this will be like a minus X prime plus X, and since this element is from kernel of A, we can rewrite it as A of X prime minus A of X prime plus, minus X, which is equal A X prime. So the first property is done, is satisfied. So now we need to prove the second property, number 2. The operator operator A naught is bounded. The operator A naught is bounded. So let me move it a little, put a comma, semicolon. Indeed, we have, let's write it down, the norm of A0, and this is x, this is plus, this is kernel of A, and close it, norm here. So of course, by the definition, I can write it down. This is the same as the A, and I can add here x plus x prime, and that's by the previous line. Maybe I shouldn't be using the same symbol, but let me write it down. For every x prime belonging to the kernel of A. So now, knowing it, that this will be by the previous remark, that does not depend on the representative, so that means simply that for any representative this will be the same value, and consequently we can just simply write it down. By the boundedness of the operator A, this is smaller than norm of A, and the norm of x plus x prime. And as you see, this is true for absolutely every element x prime from the kernel. So I can continue, I can rewrite it down, and I can write it down that A0 on x plus kernel of A close will be smaller equal, and I put here infimum for x prime belonging to the kernel of A, and put it here. This will be the norm of x plus x prime, and times norm of A, and that gives us, so this gives us exactly this distance. So that is equal, this is smaller equal, and this is definitely smaller equal than the distance. Write it down, that's the distance between x and kernel of A times the norm of A. Okay, so let's continue, and that's the norm of this x plus kernel of A in the quotient space, so put here 0 times A, and that implies, yes, indeed, this is a bounded operator. Okay, so let's make a conclusion, so put it like this, and the operator A0 now belongs to the L, and this one is E naught, which is our quotient space, to F. And we have here that the image of A naught is equal to the image of A. And that means that we need to show that the operator A has the image closed, if and only if the image of A naught is closed, and therefore we observe the next thing. The operator A naught is injective. Sorry. Not nice. Injective. Is injective. And therefore we can see it immediately, based on our experience with the previous let's say example, that so I need to move, I'm running out of place. So A0 is invalid, A0 is is, so maybe let's do it like this, has closed image of a 0 if and only if and let me write it down as an injective. This is by problem A. There exists a constant c larger than 0 such that for every, call this one like this, x naught, x tilde, which is exactly equal x cosets kernel of A, and I can write it down, x tilde norm in the quotient space is smaller than c, and this will be A0 x tilde. Now, we just simply translate this condition to the condition that we had it. So namely, notice that this norm of x tilde, so let me write it down, this is nothing else than the distance between x and the kernel of A, and the other one accordingly what we have seen before, so this will be equal c, and this will be A of x as it was used for the definition above of the operator A0. And that means basically, because here we have if and only if, that we finish this problem. So I have had fun, and I hope the solutions to these problems help. I do not prepare anything yet regarding the new material. I just decided that we should practice, let's say, this video lecturing, and in order to do it, I was thinking that the most fun we get when we are solving the problems, especially I'm getting this fun, and that's the most important for me. I like to make these presentations in such a way that I learn how to do these videos, and you will learn how to prepare yourself for the exams. And I'm pretty sure there will be exams, and especially when we have these nice ideas of solve problems. Now those are definitely all problems from the textbook, that means the Bresis textbook, that could be used on the examinations. I love to use all those problems that were, let's say, well practiced, and this is exactly an example of such a problem. So I hope you will enjoy it. And one of the best advice I can give it to you now, in the view of this global pandemic and scary situations, doing math is kind of a great refuge. It takes your mind away, and it gives you kind of a pleasure that you may feel very comfortable with. So let's continue these things. I will try to add to this presentation the part number 4. This will be part D of the lecture 1. Still, this is review of the chapter 2, and after that we will continue the chapter 3, which is dealing with the weak topologies on the Banach space E and its dual. So thank you for your attention, and I hope that you liked it. And if you like it, let me know, because it makes me pleasure that somebody is actually reading it. No reading, listen, okay, watching it, right? I should say watching it. Thank you.